So in this video, we continue our discussion of Wkb by looking at the non-classical region. First, we'll review the Wkb approximation and the solution that we got for the classical region. And we'll talk about the non-classical region. And finally, we'll talk about a simple problem of bumpy barrier tunneling. So, the Wkb approximation works for potentials that vary slowly spatially, and we assume a wave function like that of a free particle. So psi of x is equal to a of x, where the amplitude changes, and the wave number also changes, so you get e to the plus minus I k of x times x, where k of x is just the square root of 2m times quantity e minus v of x over h bar. If you remember, the Wkb approximation holds as long as the spatial derivative of the potential is small over the scale of many wavelengths, and that condition is written as follows. So you have lambda is equal to 2 pi over k, is much, much less than v of x divided by its first derivative. So if the derivative is small, this becomes large, and this condition holds. And this also holds for the case where E is less than V of x, that is the non-classical region. So that when we're in the non-classical region where the potential is bigger than the total energy, then we have psi of x is equal to a of x, e to the plus or minus kappa x of x times x. And you note that now this is not an oscillating exponential, but a decaying or rising exponential, as we might expect from what we learned about free particle tunneling in previous lectures. So kappa of x is just given by square root of 2m times v of x minus e over h bar. So we've flipped the orientation of this to make this a positive definite quantity under the square root, and that eliminates the imaginary term here. And so now you have the real exponentials. We solved the situation of the classical region, that is where we had an oscillatory function. And we got something that looked like oscillatory functions where the phase, which is up here, k of x times x, was an integral of the momentum. And the amplitude depended on a constant divided by 1 over the square root of the momentum. So that the particle would stay longer where the momentum is smaller, that is where the potential is higher compared to the energy, and less time where the momentum is larger or where the energy is higher above the potential energy, which makes perfect sense. But we treated only a system where we kept the particle confined to a classical region, that is the region where E is greater than V of x. Now we're going to solve the non-classical region. So in the non-classical region, the energy is less than the potential in all parts of the energy of the region. So from 0 to A, if we just look from 0 to A, the energy is less than V of x everywhere. Well, now the classical momentum is now imaginary because the classical momentum is given by E minus V of x. And that now is negative, p squared, right? And the square root of that is now imaginary. So p squared is 2m times E minus V of x, and that's less than 0. So we assume that the amplitude, again like before, the amplitude a of x and phase phi of x in our wave function are real and depend on x. So psi of x is equal to ax e to the I phi x. d psi dx, the first derivative is a prime plus I a phi prime e to the I phi. And the second derivative, just like before, gives us a double prime, right? The second spatial derivative of a plus 2i a prime phi prime plus I a phi double prime minus a times phi prime squared, all times e to the I phi. We take this, put on the right side my momentum squared, so I get minus p squared over h bar squared a times e to the I phi. Again, we can cancel the e to the I phi, and we get an equation which we now have to solve. But this equation contains real and imaginary components, and they can be split off. So this is the same equation we've had before, with the exception that we've hidden the fact that v is bigger than e, so that the momentum squared is negative. But that will come in shortly. So we have the red for the real equation, the green for the imaginary equation. The real equation, as before, becomes a double prime minus a times phi prime squared is equal to minus p squared over h bar squared times a. Or a double prime is equal to a times the quantity phi prime squared minus p squared over h bar squared. And the imaginary equation is 0 is equal to 2a prime phi prime plus a phi double prime. We multiply by a on both terms, and we get 2a prime phi prime plus a squared phi double prime, and this is an exact derivative of a squared phi prime. We can solve this again as before. We get the a squared phi prime stuff inside here. When we integrate this out, it's just equal to a constant because you have 0 on the other side. And we'll call that constant b squared. Or a is equal to b over the square root of phi prime. So all this is exactly as we had for the classical region. We invoke the Wkb approximation again. We let a double prime go to 0 because a double prime is going to be very small if you have a slowly varying potential. And we now write our real equation as whatever's in this brackets here, that is phi prime squared is equal to p squared over h bar squared. Now, when we take the square root, we now have to reckon with the fact that p squared is less than 0. Because p squared is less than 0, we can force a negative sign here and make this an absolute value of p squared, the modulus squared of p. So this is now an equivalence. Because we know that p squared is negative, we can force it explicitly. Now when we take the square root, we have the following differential equation. We have d phi dx is equal to plus or minus, from the square root here, and then the square root of minus 1 is I, times the absolute value of p over h bar. So now, in this non-classical solution, we've now deviated from what we had from the classical region, where this was positive, and we just didn't have an I, and this was not an absolute value, but just p. Therefore, the phase now can be solved by direct integration, and we get plus or minus I over h bar, integral of the absolute value of p of x times dx. And the wave function, remember the wave function had e to the I phi of x. Now the wave function, because of the added I here, becomes a real exponential. So we have psi of x is equal to c over the square root of now phi prime, from our definition here, it's just going to be the absolute value of p of x. And so we have that times e to the plus or minus 1 over h bar, so this is a real exponential, times the integral of the absolute value of p of x dx. So let's apply the Wkb approximation to a barrier with a bumpy top. And now we'll see how this is actually used. So we have, for the region x is less than 0, we have a free particle. Potential is 0. So we can write psi of x is a e to the ikx plus b e to the minus ikx. Totally free particle, incident wave, reflected wave. over where x is greater than a, we have just a transmitted particle. So a transmitted wave, so we'll call it psi of x is equal to f e to the ikx. Again, the potential energy is 0, so k is the same in both the first region and the region f greater than a. Now, in between 0 and a, the problem or the solution has to be the Wkb solution. And because of the approximation, we can write the psi of x is approximately equal to a constant c over the square root of absolute value of p, because the energy is below the potential there. Then you have e to the 1 over h, so it's a positive going wave, positive going decaying, rising exponential, integral of absolute value of p dx, I've hidden the x dependence here, plus d divided by the square root of absolute value of p, e to the minus I over h bar integral of p of x dx. So that would be, one would give you a rising exponential wave, and the other one would give you a decaying exponential wave. Now, in principle, you can solve this problem and you would include both c and d. But let's make an assumption to simplify this problem, that if the barrier is high, very high compared to the energy, or it's wide, so A is very large, then the coefficient C will be negligible because this is a rising exponential. It will be unlikely to have much reflected wave coming back. It's really responsible for the reflected wave coming back and transmitting back through. So we'll set C to 0. And now the reflected, which is B, and the transmitted coefficients are related by the wave function inside the barrier, which is this term here. So by integrating the momentum, which depends on x, from 0 to a, we can make a connection between f and b and a. F squared is then approximately equal to a squared times e to the minus 2h bar over integral times integral of p dx. And the transmission coefficient is going to be, because of continuity, this has to be equal to this, the amplitudes have to be equal at A, and the amplitudes have to be equal at 0 as well. And the transmission coefficient, not transmission coefficient, but transmittivity, is F squared over A squared, which is now approximately equal to e to the minus 2 over h bar integral of the momentum, absolute value of the momentum dx equals e to the minus 2 times gamma, which is this integral here, divided by h bar.